and this is okay. The overview. They model the displacement in this way, like two components. One is the trend displacement, and the other is the periodic displacement. The trend displacement, let's say they predict it using just fitting a third order polynomial, and while the periodic displacement, that is the interesting part, they used a machine learning model to predict it. And the main, let's say, the main focus of the paper is predicting this periodic displacement.
So just one. Go ahead, Davide. Yeah, please go ahead.
So they use a sort of physical model for the trend displacement.
The paper does not go very deeply in the trend displacement. The paper is mainly focused on the periodical displacement. Any other question?
Nope.
Can you put back the picture? I want to see something.
Yeah.
Where is it? Okay.
These two are the areas.
For how long they collect data?
Here it says several years. I think at least 10 years. I'm not sure. I don't remember.
And what kind of data are they collecting?
They are collecting only the displacement. Mm-hmm. And the objective was to forecast the displacement, of course. And apart this time series, they also used the rainfall precipitation time series and the water level in these two reservoirs.
Okay.
Basically, this is let's say pretty recent paper. It was published in 2019. And one important thing I think is that in literature there are many different papers which uses this data set. So the collection of data in Three Gorges Reservoir Area. Let's say past papers used a static regression model like, I don't know, SVM and so on, while they use here a LSTM model. And because they think that here they say that they think that a dynamic model could be better to capture the relationship between two different times of landslide displacements.
Basically. So what is the frequency of the data?
I don't know, but there are. I'm sure there are more. Let's say more samples per day. I don't think it is written. I don't know this particular thing.
Okay. What's the horizon of the forecasting?
Well, because
what's the horizon?
Well, because they want, if they can forecast let's say a big displacement, then maybe.
How much ahead do they want to forecast, predict?
1 week, 1 day, 1 hour?
Actually, I don't know. I don't know this.
Okay,
this
doesn't
answer.
matter. Doesn't matter. So we know that there is the problem is predicting a landslide. Okay, with I imagine.
Actually, it is not exactly predicting the landslides, but it's forecasting how much a specific GPS sensor will move due to a displacement, basically.
Yeah, so this is a proxy for the displacement.
Yeah. And okay, so for displacement discrimination factor. Okay, okay, 1 second. Okay, there are some plots of the data, very interesting. Okay, these are all the data involved. The green signal is the cumulative displacement of this ZG118. That
Can
is
you
one
make it bigger?
Yeah. 1 second. Okay. This green signal is the cumulative displacement of this sensor, the ZG118. While the other data are the red one, that is the reservoir water level, and the blue histogram is the precipitation. And it's pretty evident how all the signals are, let's say, correlated. In fact, when the red one increases, the green increases as well.
Sorry, the blue is precipitation, right?
Yeah. And another interesting correlation is the water level with respect precipitation. Every time the precipitation increases, more or less, the water level decreases. And yes.
So these are signals.
Yeah.
That are not. Go ahead.
Yeah, and the main purpose, the purpose of the paper was forecasting the green signal. Basically.
Yeah, but there is no data coming from the ground from this landslide.
No.
So this is purely based on
the signal itself, that is the green one, and on some other factors that are the reservoir water level and the precipitations.
Fine, okay. And this landslide, give me an example of a moment in time when there was a landslide or where the landslide probability is highest.
Okay, they are not predicting the probability of having a landslide. They are just forecasting the displacement.
Fine, but intuitively I can see it. I can see it there. A moment in time when
we can assume that if displacement is big, then also the landslide was, let's say, severe.
So for instance,
here,
yes.
And I don't know, here.
No, and even in 2007, right? Look, there's a big displacement.
Yeah, here, and so on. And as you can see, all these big displacement almost always occur in correspondence of high precipitation values. This.
Okay. Clear for me. David, any questions?
Yeah,
comments?
no, it's clear. Yeah.
Okay, let's move to the more interesting part, which is imagine a technical part.
Yeah. Okay, so basically the same. Okay. Okay, this is the cumulative displacement split in trend signal and the periodic signal.
Okay, hang on a second. The model. Go back to the model. I want to understand how the model is designed. So it's a prediction model.
Yeah,
And
it's a regression problem, basically.
so y of x, where x is those two variables, okay? And how is the model structured?
Yeah, it takes as input 4 time series. 2 are the trend of the displacement up to a certain point, of course. And the other is the periodic term. So these two
Yes.
data here. The other 2 time series are the precipitations and the water level.
Question for Davide. So what they do is they deseasonalize, let's say, the signal, they detrend it, and then they feed it to the model these periodic and trend terms separately. Is that correct?
Yeah, I guess that the red term is like the residual of the linear trend.
Yes.
Yeah, these 2 columns are data from 2 different sensors, but the concept here is the same. Because in particular, at the end of the paper, we will see that they tested the model on two sensors, the 118 and the 111. Yes. Okay, so they trained this LSTM. Here is written that they did a grid search to find the best parameters set. All the data were normalized between -1 and 1. And also they trained a SVM model with the same data as baseline. Okay, 1 second. Let me qualitative result. Okay, these are the qualitative results on the whole data set, basically from 2004 up to 2013. It's the measured and the predicted signals are very actually this part is the test one, and this are very similar, but there are some other interesting let's say results. Okay, now apart from here we have 1 second. Okay, here we have the quantitative results in terms of RMSE. Here that is the relative error on the test set for the LSTM model, 7.53, and this is for the SVM, so twice the LSTM. Yes.
Just one. Okay, yeah, I'll let you finish, and then some comments. We're running out of time.
Okay, these are for the one sensor, 118, and these are for the other sensor, data 111.
Okay.
And then there are some other interesting analysis. Okay, this is not. Okay. If you basically here we have the same. Basically here we have the analysis of the model performance on a specific time frame that is all the 2013, because they say that it was a particularly critical year for displacements.
Yes.
And yeah, again, the black signal is the measured one. The red is the LSTM output, so very similar to the black here, apart from this point. And the blue is the SVM. Yeah, the LSTM absolutely outperformed the SVM. And very last thing, these are this another quantitative let's say analysis of data from May to July in general, not only 2013, because this period, these 3 months are particularly, again, critical. And the LSTM is absolutely, again, better than LSTM. 7 versus 21, 10 versus 22, and so on.
I mean, this is mildly interesting because we already knew that LSTM would beat SVM. So, Davide, do you have any questions about the paper in general before we wrap up by maybe sharing our thoughts about how this is different from the problem that we are trying to face with our landslide detection?
I was pretty interested in the comparison between the SVM model and the LSTM. You say that other researchers tried to solve this problem in the past.
Yeah, I read some other papers.
I'm wondering why. I mean, LSTMs are not a very new method, so why they just tried in 2019 this method and not before?
Well, I read some papers from very old papers, so 2012, 2013, and this is the first one in terms of time that uses LSTM.
Yeah, and I guess that LSTM starts to outperform SVM when the sequence of the input data is pretty long.
Yeah, but just think about the collection of data. I think that they finished collecting data in 2013, 14. So I don't know if before or then already LSTM already exists.
Yeah.
And okay, maybe here before I show this, where is it? This actually is the qualitative result on the trend term only, while let's say the whole signal is this one, the measured versus the predicted signal. Again, they are pretty similar.
Yeah.
Okay. Any more observations or any more questions before I share my thoughts?
No. Yeah, I actually, I think that what they did with the model, doing a grid search using LSTM, is not such a big idea. It's the first idea that I would implement if I have to solve this kind of problems. So I don't know, maybe.
Okay, yeah. So there's more that could be done. That's for sure. I think that this problem, I mean, the problem related to this data set is fairly easy or easier to solve than a problem like the one that we want to solve, meaning that there is a sensor and there might be a very localized landslide or not. I mean, it looks like here we have a periodicity in the signal, we have a seasonality that makes, we have a trend, makes the whole prediction more, let's say, tractable, okay? Because I believe that in our case, the events are much more rare, they are less seasonal, they are much more non-linear, if you know what I mean.
Yeah, and most important, I think they are not predicting a landslide. Yeah. They are just forecasting the displacement, but there is one step from predicting the amount of displacement to saying what is the likelihood of having a landslide?
Yeah, here they're just they're predicting, they're forecasting the displacement. They're not detecting the anomaly, or they're not detecting the event. And we know that LSTM can be used for anomaly detection, right? Because essentially the next step would be to estimate a dynamic threshold on the top of this signal, on the top of this forecasted signal, that essentially tells you whether or not there is a landslide. Does it make any sense?
Yeah, absolutely.
And this is what we experimented with last year, right? When we were doing the same things in with, you know, in another domain, which was predicting load.
Yeah.
Excellent. Okay, guys, thanks a lot thanks a lot to Valerio to prepare this this review, and maybe we can already think about next week. What are we gonna? Is there a specific paper, David, that you want to talk about next week?
I don't know.
Okay,
I have
you
to
don't
think
know.
about it.
Oh, fair enough. All right, guys, thanks a lot. Have a good weekend.
You're welcome.